So the subject of today's lecture is Maxwell's equations in matter. Now, I want to emphasize what I said last time, which is that the vacuum equations that we've already written already contain all the physics that we could possibly desire to address. Okay, so let's just remind ourselves, and I want to emphasize this as well. Maxwell's equations are like a non-negotiable part of this course. Either you know them or you don't. You will be asked them, you have to know them. Okay, so if you're asking which equations you do need to know, I mean, there are many things that you do need to know, but you know, Maxwell's equations are really non-negotiable. So both the version in vacuum that we've discussed last time and the version in the presence of matter that we'll discuss today. So what are these? Well, you remember, and you kind of remember the names as well. So we have equations for the divergence and the curl of our two fundamental fields. Divergence of E, according to Gauss's law, is local charge scaled by epsilon 0. The divergence of the magnetic field, this is always 0 due to the lack of existence of any magnetic charge out there. Then we have our good friend Faraday, who tells us that the curl of E is related to the time dependence of the magnetic field, just with a little minus sign, the time dependent, the time derivative of the magnetic field. And then finally, we have Ampere's law complemented with the Maxwell addition for the curl of B. So what this tells us is that this is proportional to the currents flowing around in your system, J is the volume current density. But then there's also, by kind of symmetry with the Faraday law, another term, which is just mu 0, epsilon 0, dE dt. Okay, so these are things that you should be able to discuss at Christmas with your family and all these things. If you ever have children, you should begin with this, because this is really the set of equations that will be stable in time. One of the great things I liked about one of the things Feynman said, he said, look, you know, who cares about the American Revolution? Who cares about modern politics and whatnot? In 10,000 years, these are just going to be tiny details in the whole context of human history. However, Maxwell's equations will stay. They will probably endure much longer than all the other stuff that mankind is busy with. And I fully agree with this. I kind of fully am behind that thing. So, you know, whatever you do in life, just put it second before you do anything else. You should learn these equations and be completely comfortable with them. Okay, so that's the situation in vacuum. And once again, this is really absolutely everything. If we're able to really describe matter microscopically, we don't need anything else until we hit quantum mechanics. And then, of course, the whole circus restarts in a different form. We're not going to do any of that. Now, on the other hand, we have discussed the effect of electromagnetic fields on matter. And we have simplified the reaction of matter to electromagnetic fields by introducing a number of different concepts, which, if we view matter as some kind of continuous thing that can adapt, kind of marries itself with the continuum description that we have here for the electromagnetic fields. So, so what did we have? Well, for the electric case, we had the concept of polarization. Okay, so you remember how that went. Matter was essentially made of electrified constituents. These electrified constituents react to the presence of an external electric field by moving about a little bit. And then you can describe this adaptation of matter to the presence of the external field by looking at the volume density of electric dipole moments that there are in that chunk of matter as a function of position. So we had discussed this polarization vector P, which is, like I said, the volume density of the dipole moments, of the electric dipole moments. And we had related this to the bound charge density rho b by the simple relationship that the divergence of P with a minus sign gives you locally the bound density that there is. And you remember the discussion on this. So you just have maybe a non-uniform in space polarization, and that means really that there's kind of uncompensated charge as you move about. And this is the bound here. And bound in the sense that whatever you do to your system, the charges involved in the density rho bound, they might move around microscopically, but they will not start flowing like current in a wire. Okay, so that's how we distinguish that. Then for the magnetic case, we had discussed the magnetization, which is essentially the same concept. However, now for magnetic dipoles rather than electric dipoles. So we had introduced this magnetization M, and this was related to it was related to a bound current density that we denoted JB by having that the curl of M gives you this bound current. Okay, so it's precisely the same logic. You've just got local magnetization in your sample, and whatever uncompensated magnetization you have as you move around your sample represents a kind of uncompensated current inside your sample that we've called the bound current. Okay, so these are the two things that we added. So what we'll try to do is just encompass these concepts into Maxwell's equations. However, there's something new to add here. So still to add. Namely, if we have a change in the polarization, so what we're going to try to add is the time dependence. Okay, so let's just consider some very simple setup here. I've got a little cylinder like this, and I've got a polarization inside that thing. But the polarization might be changing in time. So if we first consider a uniform polarization here, then what this represents really is or what it's equivalent to, it's a surface charge on both ends here, a surface charge density. Okay, so let's say, so because of this polarization that I'd have in the bulk here, I would have here a little sigma bound. And on that side here, on the other side, I'd have just minus sigma bound. You remember that thing? I start with the uniform thing, and I'm kind of just moving the positive charges a little bit up, the negative charges a little bit down. That's equivalent then to having a bulk polarization, which is equivalent to having a positive charge on the surface here and a negative charge on the other surface here. So that's the setup that we had discussed. Okay. Yes, question. Yeah, so here, I guess what I mean is that the polarization goes this way. So that's my P here, right? And the sigma here is P dotted into the normal unit vector here, and this is my normal unit vector. Okay, so here in this very simple thing, I've put my cylinder indeed parallel to the polarization. Okay, if it wasn't parallel to that, then I just have indeed a charge on this thing here, but I'll just consider the simple setup that I have here. Okay, so if the polarization depends on time, then it's really a movement of charge, right? If I increase the polarization, then it means that I'm kind of increasing the distance between the positive and the negative charges. So while I'm changing the polarization, there is a current inside my bulk here. And this current is a genuine current, okay? Of course, I can't forever just keep flowing the polarization in a piece of matter, because the matter at some point is not going to be able to give you enough dipole density in order to do that. But while I'm increasing the polarization, there is a current moving. And this current, if you want, so let's call it a kind of little change of current delta I. What is it really? Well, it corresponds to the change of the surface charge density here. So here I'm looking per unit area. So I'm going to consider that this is a little delta A here. It's going to be proportional to the delta area that I have here. But the coefficient of proportionality is going to be just the change of the surface charge density with respect to time. So d sigma d dt. Okay. So so really, I can relate that to the change of my polarization with respect to time with this delta A here. Okay, so as I change my polarization at a certain rate, the surface charge density is going to change at that rate. Okay, so that leads us to defining a handy object which we call the polarization current density. Okay, and this polarization current density carries a very unfortunate symbol, JP. Well, you'll see why it's unfortunate in a second. And this is the time dependence of your polarization, the time derivative of your polarization. So while you're changing the polarization, where the polarization is, there is a current. Okay, and of course, when you stop changing the polarization, then this current stops. Okay, so this thing here is a real physical current, and in the presence of matter, we'll want to distinguish it once again from the free current that you're actually putting in with wires and what other means at your disposal in the lab. Okay, so one thing you really have to be careful here is not to mix concepts. So this current density here has got absolutely nothing to do with the current density associated to the magnetization. Okay, it's a completely different thing. The current density associated to the magnetization is really because of circulations of current that you have in your system. Okay, and these can be permanent. In a magnet, they will be forever there, not change. They can change in time, of course, but that doesn't induce another current. It would induce a kind of acceleration of the charges rather than just the velocity of the charges. And the equations in time are only linear, so you don't need this acceleration. But here, this polarization current is really, you change your fields applied to the chunk of matter, and the chunk of matter goes And while it goes there is charge flowing. And that's what this current is, as far as the polarization is concerned. Okay? You can verify that it obeys a continuity equation. Okay, so you can compute the divergence of JP. What is this? It's just the divergence of dP dt, which is just ddt of divergence of P, because I can invert the derivatives. Okay, and this is really just minus ddt of rho bound. Okay, so the continuity equation in this case here is ddt of rho bound plus div of the polarization current density is equal to 0. Okay, and that's why I'm saying that it's an unfortunate nomenclature here, because we would like to have the same symbol for these two things. So the bound charge is in a continuity equation with the polarization current. Okay, and here polarization current and polarization current density, they're synonyms. Okay, so same thing. Okay, so that's the kind of simple statement. So to recap, in matter, we split charges and currents as follows. So we have the charge density rho. Sorry, that's not a very good rho. We have the current density, the charge density rho. This one is going to be the free charge density plus the bound charge density. Okay, and we've seen before, we've discussed that before. This bound is just minus the divergence of the polarization like this. Okay, for the currents, we're going to split it into three pieces. There's going to be the free current density. Again, that's the stuff that you bring in as an experimentalist onto your system. And then there's going to be the bound current that comes from the magnetization. And now there's going to be the polarization current that comes from the time dependence of the polarization. Okay, so if I just rewrite these things here in terms of their definitions here, I've got the bound current that just comes from the curl of the magnetization. And now we've seen that the polarization current is just the time dependence, the time derivative of the polarization. Okay, so these are the kind of fundamental decompositions that we use for sources of electromagnetic fields in matter. Sorry, let's go down here. Okay, so these are kind of important equations. And I want to have a good green on this. Okay, this, and then, yeah, well, this whole thing. Okay, is everything kind of okay conceptually at this stage? We're not doing anything very complicated mathematically, but conceptually, this is like immensely useful. The only assumption that we're making is that it makes sense to discuss of the chunks of matter that you have in terms of things that have some smoothness associated to them as you move in space. Okay, so there's a notion of a kind of density for charge. There's a notion for a density of currents as well. Question?
Bound currents came from magnetization, right?
Bound current comes from magnetization.
That comes from a density of magnetic dipoles.
That comes from volume density of magnetic dipoles, precisely.
Polarization currents come from polarization, which comes from electric dipoles.
Yes. So this thing we've just introduced, the polarization current density, really comes from, like you say, electric dipoles. But electric dipoles that are in the process of being changed, created, enhanced, or, you know, depleted.
Well, do we have a set with both electric and magnetic dipoles? Or like the polarization, is that, because now are we talking about electric or magnetic polarization in that direction, or both?
So polarization is a purely electric concept. Polarization is purely the volume distribution of electric dipoles. Okay?
Where does the magnetic M come?
So the magnetization, the M, comes from the volume current of magnetic dipoles. So contrast two things. You have an atom, and the atom is neutral. Okay, so as you when you look at the atom, because maybe it's a simple atom, spherically symmetric shells and whatnot, it's got no dipole, it's got no electric dipole moment, just like a purely neutral thing. However, the circulation of the electrons in there, they can have a magnetic moment associated to them. So a magnetic dipole is like a tiny current loop. Okay, and this tiny current loop by Biot-Savart creates a magnetic field that is of dipole form. Okay, and this is not electric, this is purely magnetic because it produces a strong magnetic dipole moment while being electrically neutral. So magnetization is in your chunk of matter the volume density of these added up magnetic dipoles. You take a little volume, you take all the magnetic dipoles in there, you add them vectorially, you divide by the volume of that chunk, and that's big M.
So we do have magnetic dipoles.
You have magnetic dipoles possibly in your cylinder. We're not describing, we're not knowing what happens here on the magnetization. Maybe this cylinder indeed contains some magnetization going some other way. That doesn't matter here because we are looking at the density of electric dipoles, yeah, for that particular case. And in the case of time-dependent dipoles, then you get this polarization current density. Okay? You can try to think hard why you don't need a time-dependent magnetization in this description. Just look at who depends on who. Other question?
Yeah, the really long equation in the middle of the screen, pretty much.
Yes, the continuity equation.
Yeah. The divergence of P is equal to minus time derivative to.
So here what I've done is that I've used our definition of the bound charge as minus the divergence of P. So this is the density of bound charges. So from this step here to this step here, I have simply inverted the spatial and temporal derivatives. And here I've recognized the divergence of polarization as my bound charge density with a minus sign. Okay, when we introduced the polarization, we discussed that thing. So then once I've done this identification, I'm just left with this thing here. Okay, so the continuity equation for the bound charge density and the polarization current is almost like tautological. Okay, because we've essentially defined the bound charge as the remnants after having a polarization that changes in space. So we've kind of built in charge conservation there because we've done it. Okay, so it's a circular reasoning. However, at least it's consistent. The central continuity equation, which is the one for all charge and all current, that's like the mother of all continuity equations. And all the rest are consequences of that. Yeah. Other question?
Current, the EAF.
Yeah.
It comes from the magnetic dipole as well.
No, the free current is really what you would do. So you've got a setup with chunks of matter with maybe some permanent magnets in there, maybe some setup with like surfaces that have charge and whatnot. And then you come and you've got wires in your hands and you've got like, you know, or maybe you're even smarter, you're shooting charged particles at that system. You're shooting a beam of charged particles at that system. That's your free current. Okay, the free current is the stuff that really is unbound. Okay, so that's it. Okay, so then let's see where this leaves us. Now, the point is that we can easily rewrite Gauss's law. So what did Gauss's law tell us? Well, it tells us that the div E is equal to 1 over epsilon 0 rho, but rho is rho free plus rho bound. So it's this here. So it's rho free minus div of P. Okay. So what am I going to do? Well, I'm going to take this one here, and I'm just going to, maybe I should use a blue. Thought I was having blue. I'm just going to pull this one to the other side, like this. Okay, so what that means is that I can write this very same Gauss equation now as the divergence of this other object that we had introduced, the displacement. Okay, so we've seen this equation before, okay, where D is by definition epsilon 0 E plus P. Okay, so again, these are like absolute green square equations. Once again, we gotta choose this one here. Okay, so we've seen this equation, but this is now the first of the Maxwell equation in matter, the first Maxwell equation that we have in matter that we'll want to carry. Okay, so we've already seen this one. Now we can do the same with the Ampère-Maxwell relationship. So what we do is we consider now the curl of B. And this is what? This is mu zero with the total current. Okay, but the total current is the free current plus the bound current plus the polarization current. So it's just J free plus the curl of M plus dP dt. Okay. And then I've had this other term here, which was mu zero epsilon 0 dE dt. Okay, but now you see how things arrange, right? So these two here, if you put them together, they just give you, of course, with a factor of mu 0 here, they just give you the time dependence of D. Okay, and then this one here, I'm going to do the same trick as before. I'm going to pull it to the left of the equations. Okay, so what I get is that by defining a smart combination, so first of all, I'm just going to divide out by mu 0 here, and I'm going to pull this M to the other side here. So I'm going to consider the combination 1 over mu 0 B minus M. And that's a handy combination that is given a very unhandy name, H. I don't know what kind of predilection physicists have for H, but everything is H, even before the times of Hamilton. So H, again, is a field that doesn't carry a proper name. We call B the magnetic field, but actually in much of the literature, mostly in the published literature, H is called the magnetic field. Okay, so don't confuse them. Yeah, sometimes look at the context. If there's matter around and people talk about magnetization and whatnot, and they say magnetic field, typically they mean H. And then how they call B is a mystery. If I say, oh, the original magnetic or the vacuum magnetic field or something. Okay, there's no good name for it. Absolutely. So if you're in vacuum, then H is just a rescaling of B. Okay, and that's it. However, in the presence of matter, very often H is the object that you are like sensitive to. So you'll measure something, maybe with a little detector, and this little detector will detect H, not B. Okay. And H is like directly related to the free sources that you have. So maybe we just write we get the kind of equation that we can discuss a tiny bit. So what we have then from Ampère-Maxwell, we just have that the curl of H, okay, this one is just now we've divided by mu 0. There's the J free plus the dB dt, dt. Okay, so once again, glory to these equations. Okay, so this is the equivalent of Ampère Maxwell, but in the presence of matter. Question? So the mu zero, so I divide by mu zero throughout. So I obtain B over mu zero. The M just goes on the other side. And the mu zero here falls away. But yeah, you see, so I had mu zero dpdt, so now there's only dpdt. So it's so ddt of epsilon 0 e plus d plus p, which is our definition of d. Do you see what I mean? Should we do that again? Yeah, you get it? So it's just I combine this term here. So like I said with the blue line here, this term here with its mu zero factor combined with this one gives you mu zero d of d with respect to time. So that's how it goes. And then I divide by mu zero throughout and I get this. Okay, cool. Okay, so that's it. That's what we've got. Again, I keep writing so and so. So Maxwell's equations in matter, we've got them. Okay, so what are they? Well, I've got the div of D is equal to the free charge density. I've got the div of B is equal to 0. You see, this one just hasn't changed because it wasn't coupled to matter in the first place. The same thing with the Faraday law. So if I take the curl of E, this is still minus dB dt. And now the matter version of Ampère Maxwell is just the one that we wrote above. Okay, so there you have it. And now, sorry, I'm kind of bombarding you with green boxes here. Here, I'll put a thick one because it's like super duper important. Okay, so you know, that's it. The course is finished, really. The rest is just engineering, like they say. These are all the concepts that you need in order to do whatever, to solve whatever problem where you don't have any quantum mechanics to bother with, and it's a good approximation to think of your chunks of matter as smooth, differentiable distributions of charge and current. Okay? Yeah, is that cool? And maybe one nomenclature, maybe so NB, oops. So the dd dt is known, sorry, as the displacement current. Okay, that's just nomenclature for this. Okay, so D, the time dependence of D is the displacement current. Again, you'll come across that term in the literature. Question?
Displacement current was epsilon 0 times the time dependence B.
Yeah, so you see here, it's essentially the same thing, except that we've added to it the polarization. So in the discussion that we had before, you remember with the charging capacitor and the changing electric field, we also called it the displacement current, which was technically correct, provided there was nothing but vacuum between the plates. Yeah, always like that phrase, you know, so the space between the plates was filled with vacuum. So it's like, well, it's a wonderful concept. Only physicists can appreciate that. So it's the same definition, except that back then I did not tell you that it had a kind of generalization to the presence of matter, provided you took your polarization current into account. So now it's the same thing. So that's the kind of proper final definition of this displacement current. The earlier one was still valid, but again, you didn't know back then just how smart you would be with these things. It was technically correct. You would not be sued. You would like fulfill all legal conditions associated to the displacement current back then. But now you know better. Okay. So it's the kind of same object. So sometimes you'll see indeed JD instead of DD/DT. Okay, but it's the same thing. Okay, so that's the thing. Now maybe a quick note. So there's something missing still. It's the relation between the pairs of fields. You see, the original Maxwell equations, they're kind of cool because you've got E and B in 4 equations. But now I've got E, B, D, H. Huh? So I've got 4 equations for 4 like vector fields like that. But it's not like I've got 4 vector fields. They're kind of related to each other. So there has to be a relationship between essentially E and B and the D and H. Okay, and the point is that this relationship depends on the circumstances. So it depends on circumstances, long word, And when I say circumstances here, I mean the precise nature of the junk you're dealing with, right? There's a very simple case. What we've called linear media. And you remember what that was? This was matter in which the polarization was proportional to and in the direction of the applied electric field, and the magnetization was proportional to and in the direction of the applied magnetic field. So in those cases, what did we have? We had the polarization vector being given by some susceptibility times the electric field. And we had a magnetization which was proportional to some magnetic susceptibility times the applied field. And in this case here, be careful, because just by historical accident, the definitions are not quite symmetrical. Here, M is not proportional to B, but it's proportional to H, which already contains M inside. Okay? But it still works out because it's a linear relationship. So it's just a definition of the meaning of the susceptibility. Electrical susceptibility was defined historically way before the magnetic susceptibility, and the parallels, I guess, were not like completely clear back then. So historically, this is how it came to be. And in that case, what you have is that the displacement D just becomes proportional to E. Okay, and this susceptibility here is like epsilon 0, 1 plus electric susceptibility here. And then H is equal to 1 over mu times B, where mu 0, 1 plus chi m. Okay, that's the way it's so I emphasize this is not universal. This doesn't always work. Okay, in fact, in a sense, you can say that it never truly works. If you're looking at arbitrary precision, there will always be corrections to that. However, it might be dominated by this linear aspect of the response of your system to the presence of these external fields. Okay, with the notion that you have a linear medium and within this approximation, then you can go much further. If you don't have this relationship here, then you have to characterize your material better. Okay, so these relations, they're known as constitutive relationships, and these you would really have to experiment with the particular types of matter you're interested in order to properly characterize these things. Okay, so that's the kind of statement. So this is really like an aside. We'll come back to it because we will be working exclusively with linear media when we actually do applications of this.